As you can see, I'm a busy student and I am hungry. And I only have a few minutes before I have to leave for an exam. But I don't know if a pan, boiling water, or a microwave will heat my tofu to the temperature my mouth desires the fastest. In this video, we will explore topics of conduction, convection, and radiation as it applies to different cooking methods.
Cooking is probably the most common way most of us take advantage of all three types of heat transfer, so it's perfect for demonstrating the key differences between each of them. First is conduction. Conduction is exemplified by pan frying or pan roasting different foods on a stovetop. Conduction relies on a solid medium as a means of heat transfer. Faster moving molecules bump into slower moving molecules immediately next to them and transfer kinetic energy. Next is convection. Convection is normally encountered in the form of boiling water in convection ovens. Convection is the transfer of heat via a moving fluid medium. Here, the key difference from conduction isn't just the use of fluid medium, but heat transfer due to the bulk movement of the fluid medium. Finally, there's radiation. A microwave is a great example of radiative heat transfer. Radiative heat transfer is due to the absorption of electromagnetic radiation, meaning light. Unlike conduction and convection, radiation does not require any medium. Now, let's dive into the experiment that will help you figure out how you should cook your tofu.
For this experiment, we needed a few pieces of equipment. We needed a thermometer, a set of pots and pans, a working microwave, a stopwatch, and of course, a block of tofu. Additionally, you can't forget water, something to heat the pots and pans, such as a stove or a hot plate, and paper towel to place the tofu on in the microwave. In this experiment, we took 3 identical 1-inch cubes of tofu and heated each of them from the same initial temperature to the same final temperature using the 3 different methods of heating transfer. Using the standard heat transfer equation, Q equals mCp delta T, we know that the total heat absorbed by each cube is the same. We then measured how much time it took the center of the tofu to reach the final temperature by heating the tofu through the use of pan frying, boiling, and a microwave. To ensure that the other conditions were constant, we had to control a few aspects of the experiment. First, for our conductive heat transfer demonstration, we had to keep the pan at a constant temperature of 100 degrees Celsius. Additionally, for our demonstration of radiative heat transfer in the microwave, we placed the tofu on a paper towel to limit the amount of heat conducted through the bottom of the microwave.
Our predicted outcome of the experiment was that the microwave would bring our tofu to 80 degrees Celsius the fastest since there is no medium for which heat is lost. Then we thought convection would be faster than conduction due to a moving fluid medium having more kinetic energy than a solid medium, which leads to faster heat transfer. In our experiment, we measured the time it took for each block of tofu to have a constant change in temperature of 65 degrees Celsius internally. Using the equation Q equals mc delta T, along with the tabulated constants of mass and specific heat, as can be seen in the table, we were able to find that each cube of tofu absorbed 3.63 kilojoules of heat energy. Radiation from the microwave took 120 seconds, next was convection from boiling water that took 420 seconds, and last was conduction from our pan, which took 2,400 seconds. As you can see, our prediction was correct, as the microwave was a much faster and efficient mode of heat transfer for this scenario. This experiment exemplifies the differences between the forms of heat transfer and does not claim that radiation is the best form for every type of food, but will provide the fastest heat transfer. Although we did our best to hold several different variables constant over the course of our experiment, it is difficult to reduce a cooking method entirely down to one mode of heat transfer. For instance, when pan cooking the tofu, it is very difficult not to have convection also take place within the system. Additionally, to ensure that each cube of tofu took in the same amount of heat, we had to hold the temperature change constant over the course of the heating period, which meant that we had to check the temperature at several different times. This required us to bypass our controls to isolate heat transfer methods each time we needed to check the temperature as well. Chemical engineers have to think about heat transfer all the time. They use their knowledge to design better heating and cooling systems, design safety precautions, improve sustainability, and of course, become better cooks. Conduction, convection, and radiation, in general, have their proper applications for everyday engineering. For example, furnaces employ radiation as its main form of heat transfer to melt or heat up materials in factories and plants. They can design cooling fins, which utilize increased surface area and convection to cool down objects. And insulation utilizes conduction to keep our houses warm during the wintertime.
Crispy and delightful.